So I'm gonna read this for 1 hour today, I believe. And then I'm gonna do some other stuff off stream. Boolean values. In real life, it's common to ask or be asked questions that can be answered with yes or no. Now consider a similar statement that can be answered with a true or false. These kinds of sentences that have only two possible outcomes are so common that many programming languages include a special type for dealing with them. Boolean variables are variables that can have only two possible values, true or false. To declare a Boolean variable, we use the keyword bool. To initialize or assign a true or false value to a Boolean variable, we use the keyword true or false. Just as the unary minus operator can be used to make an integer negative, the logic not operator can be used to flip a Boolean value from true to false, or false to true. Boolean values are not actually stored in Boolean variables as the words true or false. Instead, they are stored as integers. True becomes the integer 1 and false becomes the integer 0. Similarly, when Boolean values are evaluated, they don't actually evaluate true or false. They evaluate the integers 0, false, or true 1. Because Booleans actually store integers that are considered an integral type. Printing Boolean variables. When we print Boolean values with standard count or standard count prints 0 or false and 1 for true. Yeah, that's what was happening there on the course. On some exercises. If you want standard count to print true or false instead of 0 or 1, you can use standard bool alpha. Here's an example. So this prints true or false. You can use standard no bool alpha to turn it back off. Integer to Boolean conversion. You can't initialize a Boolean with an integer using uniform initialization. Normal conversions disallowed. Note some versions of G++ don't enforce this property. However, in any context where an integer can be converted to a Boolean, the integer 0 is converted to false, and any other integer is converted to true. So 0 is false, the rest is true. Inputting Boolean values. Inputting Boolean values using standard character in sometimes trips new programmers up. Consider the following program. Enter a Boolean value. True, you enter 0. Wait, what? So it's because it's converting. It turns out that standard character in accepts two inputs for Boolean variables 0 and 1, not true or false. Any other input will cause standard character in to silently fail. In this case, because we entered true, silently failed. A failed input will also zero out the variable, so B also gets assigned value false. Consequently, when standard count prints a value for B, it prints 0. To make standard character in accept false and true as inputs, the standard bool alpha option has to be enabled. However, when standard bool alpha is enabled, 0 and 1 will no longer be treated as booleans. Boolean return values. Boolean values are often used as the return values for functions that check whether something is true or not. Such functions are typically named starting with the word is equal or has. Consider the following example, which is quite similar to the above. Turns true if x equals y, and false otherwise. This is asking for integer 2 times equals a false. Then using is equal here. return true or false. Here's output from true runs of this program. How does this work? First, we read integer values for x and y. Next, the expression is evaluated. In the first run, this results in a function called 3 is equal 5. Inside that function, 5 equals 5 is evaluated, producing the value true. True value is returned back to the caller to be printed by center count. The second run, the call to is equal 64 returns the value false. Boolean values take a little bit of getting used to, but once you get your mind wrapped around them, you're quite proficient in their simplicity. Boolean values are also a huge part of the language. You end up using them more than all the other fundamental types put together. Introduction to if statements. Consider a case where you're going to the market and your roommate tells you if they have strawberries on sale, buy some. It's a conditional statement, meaning that you execute some action by some, only if the condition is true. Such conditions are common in programming as they allow us to put more conditions. I think this is basic stuff. Given the following program, here's the output. Let's examine how this works in more detail. First, the user enters an integer. I don't think I need to read this, quite redundant. If else, training statements. Boolean returns value in if statements. We wrote this program is a function that returns a Boolean value. Let's improve this program using if statements. Non-Boolean conditions. In all of the examples above, our conditions have been either Boolean values true or false. What happens if your conditions is an expression that does not evaluate your Boolean value? So it's far. This will print high since far is non-zero. Value that gets converted to Boolean true, causing this statement attached to the if to execute. We continue our exploration of if statements in future class. Quiz time. A prime number is a whole number greater than 1 that can only be divided evenly by 1 in itself. Our problem that asks the user to enter numbers 0 to 9 inclusive if the user enters within the range that is prime, digits prime, otherwise I'm not gonna do that. Already did that on other courses. To this point, the fundamental data types we've looked at have been used to hold numbers. Integers and floating points are true or false, but what if bunch star letters are punctuation? The char data type was designed to hold a character. A character can be a single letter, number, symbol, or white space. The char data type is an integral type, meaning the underlying value is stored as an integer, similar to how a Boolean value 0 is interpreted as false and non-zero is interpreted as true. Integers stored by a char variable are interpreted as an ASCII character. Stands for American Standard Code for Information Interchange, and it defines a particular way to represent English characters plus a few other symbols as numbers between 0 and 127, called this acronym code or code point. Example code is 97, interpreted as the character A. Character literals are always placed between single quotes. Here's a full table of ASCII characters. So there's a bunch of characters here. I don't think I'm gonna print this. Maybe I should print. So this is the way that each of these characters is stored in memory, if I getting this correctly. I might be good to take a picture, because why not? Then I'm gonna store it in the same file. Code 0 to 31 and call the variable char. Initializing chars. You can initialize char variables using character literals. Initialize chars with integers as well, but this should be avoided if possible. Warning, be careful not to mix up character numbers with integer values. The following two initializations are not the same. Character numbers are intended to be used when we want to represent numbers as text, rather than as numbers to apply mathematical operations to. Intended to be used when we want to represent numbers as text, rather than as numbers to apply mathematical operations to. Printing chars. When using standard count to print a char, standard count outputs the char variable as an ASCII character. This produces the result AB. So character 1 prints this. 1 is because it's creating the character here. Code point for B, not preferred. Count prints a character B. So this prints B. This creates B. C98B. So you do need to memorize not memorize, but know the chart. You can also output char literals directly. This produces these results. See. Inputting chars. The following program asks the user to input a character, then prints out the character. Yeah, one thing that I'm thinking about is after I read this book is going back to Chicago and doing pandas and also studying the NumPy library more because I've been using that quite a lot and I think it's good to review some concepts. I think that so far from my experience, those are the most important ones that I use the most often is understanding pandas, how to manipulate the data frames, and NumPy arrays. I think is good. So I might add that to the list of things that I'm gonna do before I even do the build my own AI libraries, and then maybe go back and do some other courses as well, some of the machine learning courses again. I think I'm gonna put it here. In the book, and I think either Saturday or Monday I'm gonna probably try to read a bunch of hours of the book so I finish faster. Finish Escalao, revisit Chicago. Here's the output from the run. Note their standard character will let you enter multiple characters. However, variable ch can only hold one character. Consequently, only the first input character is extracted into variable ch. The rest of the user input is left in the input buffer that standard character uses. and can be extracted with subsequent calls to standard character in. You can see this behavior in the following example. Assume the user enters UCD without quotes. If you want to read in more than one character at a time, within a name, a word, or a sentence, you want to use a string instead of char. A string is a collection of sequential characters, and thus it can hold multiple symbols. We discuss strings in the upcoming lesson. Char size, range, and default sign. Char is defined by C++ to always be 1 byte in size. By default, a char may be signed or unsigned, though it's usually signed. If you're using chars to hold ASCII characters, you don't need to specify a sign, since both signed and unsigned chars count values between 0 and 127. If you're using a char to hold small integers, something you should not do unless you're explicitly optimizing for space, should always specify whether it is signed or unsigned. A signed char can hold a number between -128 and 127. An unsigned char can hold a number between 0 and 255. Escape sequences. There are some characters in C++ that have special meaning. These characters are called escape sequences. An escape sequence starts with a backwards backslash. I'm not sure if just backslash, probably just backslash character. And then a following letter or number. You've already seen the most common escape sequence, \n, which can be used to embed new line. Yeah, this is pretty redundant stuff. Makes an alert such as beep, new line. What's the difference between putting symbols in a single and double quotes? Single chars are always put in single quotes. A char can only represent one symbol. The letter A, the plus symbol, the number 5, something like this, is illegal. Text put between double quotes hello world is treated as a string. As an aside, the term deprecated means still supported but no longer recommended for use because it has been replaced by something better or is no longer considered safe. Introduction to type conversion static cast. Type conversion. Consider the following program. The above example, the print function has a parameter of type double, but the caller is passing the value 5, which is of type int. What happens in this case? In most cases, C++ will happily convert values of one fundamental type to another fundamental type. The process of converting a value from one type to another type is called type conversion. Thus, the int argument 5 will be converted to double value 5.0 and then copied into parameter x. The print function will print the value. This value will result in the following outputs. Yeah, so I think this part is important and is new for me. When the compiler does type conversion for us, we call this implicit type conversion. Explicit type conversion. Although implicit type conversion is sufficient for most cases where type conversion is needed, there are a few cases where it is not. Consider the following program, which is similar to the example above. In this program, we've changed print to take an int parameter, which is this function here. And the function call to print is now passing a double. Similar to double, the compiler you use implicit type conversion in order to convert double value into a value of type int, so that it can be passed to a function print. It's gonna discard the 0.5 from the value. Unlike the initial example when this program is compiled, your compiler will generate some kind of warning about a possible loss of data, and because you have treated warnings as errors turned on, your compiler will abort the compilation process. Tip: you need to disable treat warnings as errors temporarily if you want to compile this example. Uncompile and run this process will print 5. Note that although we passed the value 5.5 key inside, Same-type conversions are always safe to make, such as int to double, whereas others may result in the value being changed during conversion, such as double to int. Unsafe implicit conversions will typically either generate a compiler warning, or in the case of brace initialization, an error. This is one of the primary reasons brace initialization is the preferred initialization form. Brace initialization will ensure we don't try to initialize a variable with initializers that will lose value when it is implicitly type converted. Okay, int to double is safe, and then 0. Related content. Implicit type conversion is a meaty topic. We dig into this topic in more depth in future lessons, starting with lesson 8.1. An introduction to explicit type conversion via the static cast operator. Back to our most recent print example, what if we intentionally wanted to pass a double value to a function taking an integer, knowing that the converted value would drop any fractional component. Any off-treat warning as a error should just make our program compile is a bad idea, as it might open the door for other issues to slip through. C++ supports a second type of type conversion called explicit type conversion. Explicit type conversion allows the programmer to explicitly tell the compiler to convert a value from one type to another type, and that will take full responsibility for the result of the conversion, meaning that if the conversion results in the loss of value, it's our fault. To perform an explicit type conversion, in most cases we will use the static cast operator. The syntax for the static cast looks a little funny. Static cast takes the value from an expression as input and returns the value converted into the type specified by new type, int bool char double. Key insight: whenever you see C++ syntax excluding the preprocessor that makes use of angled brackets, the thing between the angled brackets will most likely be a type. This is typically how C++ deals with concepts that need a parameterizable type. Let's update our prior program using static cast. So it puts int inside and then 5.5. Because we are now explicitly requesting that double value 5.5 be converted to an int value, the compiler will generate a warning about possible loss of data upon compilation, meaning we can treat warnings as errors enabled. Data content: C++ supports other types of casts. We'll talk more about the different types of casts in the future lesson. Using static cast to convert char to int. Forgot to type this. In the lesson on chars, we saw that printing a char value center count results in the value being printed as a char. This prints A. If you want to print the integral value instead of the char, we can do this by using static cast to cast the value from a char to an int. This prints A has this value 97. So you use static cast int and then through the char. It's worth noting that the argument to static cast evaluates as an expression. When we pass in a variable, that variable is evaluated to produce its value, and the value is then converted to the new type. The variable itself is not affected by casting its value to a new type. In the above case, variable char is still a char and still holds the same value even after we've cast its value to an int. So it doesn't change, casting doesn't change the value, the initial value. Converting unsigned numbers to signed numbers. To convert an unsigned number to a signed number, you can also use the static cast operator. The static cast operator doesn't do any range checking, so if you cast a value to a type whose range doesn't contain that value, undefined behavior will result. Therefore, the above cast from unsigned int shows int will yield unpredictable results if the value of the unsigned int is greater than the maximum value a signed int can hold. The static cast operator will produce undefined behavior if the value being converted doesn't fit in range of the new type. Standard int 8 and standard uint8 likely behave like chars instead of integers. As noted in lesson fixed with integers and size t, most compilers define and treat standard int8 and standard uint8 and their corresponding fast and least fixed with types identically to types sign char and sign char, respectively. Now that we've covered what chars are, we can demonstrate where this can be problematic. Because standard int8 describes itself as an int, you might be tricked into believing that the above program will print the integral value 65. However, on most systems, this program will print a instead, treating my int as a signed char. However, this is not guaranteed. On some systems, it may actually print 65. So this doesn't print 65. Not sure if I completely understand. Because standard int8, oh, it's the type here. Is int8, I didn't see the 8 there. Describe itself as an int, you might be tricked into believing that the program will, because 65 passes the range of int8, maybe. However, on most systems, this program will print a instead, treating my int as a signed char. However, this is not guaranteed. If you want to ensure that standard int8 or standard int8 object is treated as an integer, you can convert the value to an integer using static cast. In cases where standard int8 is treated as a char, input from the console can also cause problems. I still have a question though, that I think if you want to perform mathematical operations on this, you probably can, but yeah, but I'm not sure. Simple run this program, because after you convert, the initial value is not changed, but it might be possible for the after the conversion to be used as an integer instead of the initial value. A sample run of this program. Here's what's happening. Here's what's happening when standard. Here's what's happening. When standard int8 is treated as a char, the input routines interpret our input as a sequence of characters, not as an integer. So when we enter 35, we're actually entering two chars, 3 and 5. Because a char object can only hold one character, the 3 is extended, the 5 is left in the input stream for possible extraction later. Because the char tree has is this code, because code point 51, the volume 51 is stored in my int, which we then print later as an int. Contrast the other fixed with types will always print an input as integral values. Quiz time, write a short program where the user is asked to enter a single character, print the value of the character. This program should output show solution. And maybe I should be doing this challenges here. It's just that this doesn't seem that interesting to me, because I don't know how useful it is in practice. Introduction to a standard string. The very first C++ program you wrote probably looked something like this. So what is Hello World exactly? Hello World is a collection of sequential characters called a string. C++, we use strings to represent text such as name, addresses, words, and sentences. String literals such as Hello World are placed between double quotes to identify them as strings. Because strings are commonly used in programs, most modern programming languages include a fundamental string data type. In C++, strings aren't a fundamental type, they're actually a compound type, and defined in the C++ standard library rather than as a part of the core language. But strings are straightforward and useful enough that we'll introduce them here rather than wait until the chapter on compound types. Standard string. Choose strings in C++. We first need to include this string header to bring in the declarations for standard string. Once that is done, we can define variables of type standard string. So I thought on the IO library you already had string. Just like normal variables, you can initialize or assign values to strings as you would expect. Note that strings can hold numbers as well. In string form, numbers are treated as text, not as number, and thus they can, String output, strings can be output as expected using standard count. This prints, empty strings will print nothing, which prints this. String input with standard charactering. Using strings with standard charactering may yield some surprises. Consider the following example. Here's the results from a sample run of this program. That isn't right. What happened? It turns out that when using operator to extract a string from charactering, operator only returns characters up to the first white space it encounters. Any other characters are left inside standard charactering, waiting for the next extraction. This won't work. Expect to see standard charactering based on white space. I didn't know that, so that's useful to know. So when we use operator to extract the string variable into name, only J1 was extracted, leaving the do inside standard charactering. When then used operator to get variable age, it extracted do instead of waiting for us to input an age. Then the program is done. Then the program ends. Use standard getLine to input text. Read a full line of input into a string. You're better off using their standard getLine function instead. Standard getLine takes two parameters. The first is standard character in, the second is your string variable. Here's the same program as above using standard getLine. Read the full line into text name. Just call the function and then standard getIn, standard WS name. Now our program works as expected. What the heck is standard? Yeah, that was what I was wondering. Last time we discussed output manipulators, which allow us to alter the way output is displayed. The last time we used the output manipulator function standard set precision, changing the number of digits of precision that standard count displayed. C++ also supports input manipulators which alter the way that input is accepted. The standard WS input manipulator tells standard charactering to ignore any leading white space. Explore why this is useful. Consider the following program. Here's some output from this program. So it's asking for input starting choice. Then is using the getLine but without standard. It's gonna print hello, then doesn't print the number. You pick two. So it has the choice, but it doesn't print the string. It prints true here. Pick one or two, true. Now enter your name. Yeah, so it doesn't print the name. This program first asks you to enter one or two and waits for you to do so. All good so far. It will ask you to enter the name, however, it won't actually wait for you to enter your name. Instead, it prints the hello string and then exits what happened. It turns out when you enter a value using operator standard counting, not only captures the value, it also captures the new line character. That occurs when you hit the enter key. So when we type true and then hit the enter, standard character in gets the string true on new line. It then extracts the true variable choice, leaving the new line character behind for later. Then when standard get line goes to read the name, it sees \n is already in the string, and figures we must have previously entered an empty string. Definitely not what was intended. We can amend the above program, choose the standard WS input manipulator. So standard get line to ignore any leading whitespace characters. Now this program function as intended. Best practice, if using standard get line to read strings, use the standard WS input manipulator to ignore leading whitespaces. Key insight, using the extraction operator with standard character in ignores leading whitespace. Standard line does not ignore leading whitespace unless you use input manipulator standard WS. Oh, so this operator automatically does that, but when you're using the function, it doesn't. So you have to put it there. Cool. String length. If you want to know how many characters are in standard string, you can ask the standard string for its length. Syntax for doing this is different than you've seen before, but it's pretty straightforward. So to get length, you just dot length. Note that instead of asking for the string length as length my name, we say my name.length. The length function isn't a normal standalone function, it's a special type of function that is nested within standard string called a member function. Because length member function is good to search later. The length function is a normal function, is a special type of function that is nested within standard string called a member function. Because length lives within standard string, it is sometimes written as standard string length in documentation. We'll cover member functions, including how to write your own in more detail later. Okay, so let me erase this. Also note that standard string length returns an unsigned integral value, most likely size t. If you want to assign the length to an int variable, you should static cast it to avoid compiler warnings about signed and unsigned conversions. So it's always good to cast to convert to an integer. Conclusion, standard string is complex, leveraging many language features that we haven't covered yet. Fortunately, you don't need to understand this complexities to use standard string for simple tasks like basic string input and output. Encourage you to start experimenting with strings now, and we'll cover additional strings capabilities later. Quiz time, question 1. Write a program that asks the user to enter their full name and their age. As output, tell the user the sum of their age and the number of letters in their name. For simplicity, count spaces in the name as a letter. Reminder, standard string length returns an unsigned int. You should static cast this to an int right? The age so you don't mix signed and unsigned values. So it takes 3 outputs, 1 string integer, then sums the length with the thing. I don't think I'm gonna do this. It's gonna jump to the next one. I'll probably need to review these concepts for sure when I'm doing my own thing. And I'm probably gonna research this a lot, but I don't think it's worth stopping just to make the program. I'm gonna get some water, I'll be right back. You're gonna have so many troubles with strings later in C++ line. Yeah, I imagine. But I don't think it's worth it to stop just to do the exercises. Maybe I'm wrong, but it's just that there's too much stuff to learn and not a lot of time. So I gotta be smart with my time allocation. So I make sure I'm going back and forth between all the things, because if you study everything one thing at once, then you're not gonna retain the information. And it's better to spread out the exposure between different concepts. So since I'm learning a lot of stuff, I think it's better to go back, get as much exposure as possible in the longest amount time frame as possible. Yeah, I know. I know from the previous languages as well. It's really strings, array, manipulation, objects, pretty much the core of everything. Literals. In programming, a constant is a fixed value. It may not be changed. C++ has two kinds of constants, literal constant and symbolic constant. We cover literal constants in this lesson, symbolic constants in the next lesson. Literal constants, usually just called literals, are values inserted directly into the code. So 5 is an integer literal, true is a Boolean literal. They are constants because their values cannot be changed dynamically. You have to change them, and then recompile for the change to take effect. Just like the objects have a type, all literals have a type. the type of a literal is assumed from the value and format of the literal itself. By default, integral value 50 minus 3, int, boolean is bool, floating is double, not float, char is char, and then C-style string const char. The default type of a literal is not. If the default type of a literal is not as desired, you can change the type of a literal by adding a suffix. So suffix for unsigned, long, UL unsigned. I'm gonna take a picture of this as well, because it's worth it. Should remember this. You generally won't need to use suffixes for integer types, but here are examples. By default, floating point literal constants have a type of double. To make them float literals instead, the f or f suffix should be used. Floating point literals constants have a type of double. To make them float literals instead, also to change from double to float, you put the f. New programmers are often confused about why the following doesn't work as expected. Because 4.1 has no suffix, it's treated as a double literal, not a float literal. When C++ defines the type of a literal, it does not care what you're doing with the literal. G in this case, using it to initialize a float variable. Therefore, the 4.1 must be converted from a double to a float before it can be assigned to a variable f, and this could result in a loss of precision. Literals are fine to use in C++ code so long as their meanings are clear. This is most often the case when used to initialize or assign a value to a variable, do math or print some text to the screen. In lesson 4.11 chars, we defined a string as a collection of sequential characters. C++ supports string literals. String literals are handled strangely in C++ for historical reasons. For now, it's fine to use string literals to print text with standard count or as initializers for a standard string. We'll talk more about string literals in future lessons. Scientific notation for floating point literals. There are two different ways to declare floating point literals. In the second form, the number after the exponent can be negative. So 6.2 is a double literal. 3.4 is a double literal. In the second form, the number after exponent can be negative. 1.6. Yeah. Octo and hexadecimal literals. In everyday life, we count using decimal numbers, where each numerical digit can be from 0 to 10. Decimal is always called base 10, because there are 10 possible digits. In this system, we count like this. By default, numbers in C++ programs are assembled to be decimal. 12 is assumed to be a decimal number. In binary, there are only two digits, 0 and 1, so it's called base 2. Binary count like this. There are two other bases that are sometimes used in computing octal and hexadecimal. Octal is base 8, that is the only digits available are 0 to 8. In octal, we count like this. So goes to 8, then starts at 10. Nodes, no 8 and 9, so we skip that. To use an octal literal, prefix your literal with 0. 0 for the number means this is octal. Yeah, makes sense because yeah, so but yeah. It's good to know this. Because I'm never gonna put 0 before unless it's with a dot later. By 10 instead of 12 because numbers are printed in decimal and 12 octal equals 10 decimal. Octal is hardly ever used and we recommend you avoid it. Hexadecimal is base 16. Hexadecimal will count like this. Choose a hexadecimal literal, prefix or literals 0 with 0x. Yeah, just like in memory. This program prints 15. Because there are 16 different values for a hexadecimal digit, we can say that a single hexadecimal digit encompasses 4 bits. Consequently, a pair of hexadecimal digits can be used to exactly represent a full byte. Consider 32-bit integer value this huge number. Because of the length and repetition of digits, that's not easy to read. In hexadecimal, the same value would be 3A, 7F, 98, 26. This makes hexadecimal values useful as a concise way to represent value in memory. For this reason, hexadecimal values are often used to represent memory addresses or raw values in memory. For C++14, there is no way to assign a binary literal. However, hexadecimal pairs provide us with a useful workaround. C++14 binary literals and digit separators. In C++14, we can assign binary literals by using the 0b prefix. Because long literals can be hard to read, C++14 also adds the ability to use a quotation mark as a digit separator. If our compiler, so here, if our compiler isn't C++14 compatible, our compiler will complain if you try to use either of these. Printing decimal, octal, hexadecimal, and binary numbers. By default, C++ prints values in decimal. However, you can tell that you're printing other formats. Printing decimal, octal, or hex is easy via use of standard dec, standard oct, and standard hex. I wonder how practical is this, how often people do this in real programs. But it seems like a good thing to know because memory addresses are in hex, so maybe there are some applications that are with pointers and this kind of stuff. Printing in binary is a little harder as standard count doesn't come with the capability built in. Fortunately, the C++ standard library includes a type called standard bitsat that will do this for us. In the bitsat header, choose standard bitsat, we can define a standard bitsat variable and tell standard bitsat how many bits we want to store. The number of bits must be a compile time constant. Standard bitsat can be initialized with an unsigned integral value in any format, including decimal, octal, hex, or binary. You can also create a temporary anonymous standard bitsat to print a single value. In the above code, this line creates a temporary standard bitsat object with 4 bits, initialize it with 0b, then prints the value in binary, and then discards the temporary standard bitsat. Also print from standard bitsat directly. Magic numbers and why they are bad. So consider the following snippets. A number such as the 30 in the snippet above is called a magic number. Magic number is a literal, usually a number in the middle of the code that does not have any context. What does 30 mean? Although you can probably guess that in this case it's the maximum number of students per class, it's not absolutely clear. In more complex programs, it can be very difficult to infer what a hard-coded number represents, unless there is a comment to explain it. Using magic numbers is generally considered bad practice because, in addition to not providing context as to why they are being used for, they pose problems if the value needs to change. Let's assume that the school buys new desks that allows them to raise the class size from 30 to 35, and our program needs to reflect that. Consider the following program. To update our program, choose the new classroom size. We'd have to update the constant 30 to 35. But what about the call to set max? Does the 30 have the same meaning as the other 30? If so, it should be updated. If not, it should be left alone. Or we might break our program somewhere else. If you do a global search and replace, you might inadvertently update the argument of setMax when it wasn't supposed to change. So you have to look through all the code for every instance of the literal 30 and then determine whether it needs to change or not. That can be seriously time consuming and error prone. Although we say magic numbers, this affects all kinds of values. Consider this example. So have an input, standard count, calculating input. If input bigger or greater than 100, standard count, divide the input number to be less than 100. There's only one number 100 in this example. It is also used in the strings. If we decide to update the maximum to, let's say, 200, we have to update 3 different occasions of 100. Yeah, so here and here. Fortunately, better options, symbolic constants exist. We'll talk about those in the next class. So, yeah, why not put this into a variable though? Make this equal to a variable. Oh, but it is equal to a variable here, which is max student. Not sure I completely understand that, but constexpr, and symbolic constants. Const variables, so far, all of the variables we've seen have been non-constant. That is, their value can be changed at any time. For example, can be changed to 5. However, it's sometimes useful to define variables with values that cannot be changed. For example, consider the gravity of Earth near the surface, 9.8 meters per second square, seconds to the power of 2. This isn't likely to change anytime soon, and if it does, you'll likely get bigger problems than learning C++. Defining this value as a constant helps ensure that this value isn't accidentally changed. To make a variable constant, simply put the const keyword either before or after the variable type, like so. Although C++ will accept const either before or after the type, we recommend using const before the type because it better follows standard English language convention where modifiers come before the object being modified. E.g., a green ball, not a ball green. Const variables must be initialized. Const variables must be initialized when you define them, and then that value cannot be changed via assignment. Note that const variables can be initialized from other variables, including non-const ones. Const function parameters. Const can also be used with function parameters. So here. Making a function parameter const enlists the compiler help to ensure that the parameter's value is not changed inside the function. Note that we did not provide an explicit initializer for our const parameter. The value of the argument the function can call will be used as the initializer in this case. When arguments are passed by a value, we generally don't care if the function changes the value of the parameter, since it's just a copy that will be destroyed at the end of the function anyway. For this reason, we usually don't const parameters passed by value. But later on, we'll talk about other kinds of function parameters, where changing the value of the parameter will change the value of the argument passed in. For these other types of parameters, use of const is important. Runtime versus compile time constants. C++ actually has 2 different kinds of constants. Runtime constants are constants whose initialization values can only be resolved at runtime. when your program is running. The following are examples of runtime constants. X is a runtime because the value is unknown until the program is run. And user age is a runtime constant because the value is unknown until the program is run. Variables such as user age and X in the above program above are runtime constants. It's scary. Because the compiler can determine their initial values until the program is actually run, user age relies on user input, which can only be given at runtime, and X depends on the value passed into the function, which is only known at runtime. However, once initialized, the value of these constants can't be changed. Compile time constants are constants whose initialization values can be determined at compile time when your program is compiling. The following are examples of compile time. Compile time constants enable the compiler to perform optimizations that aren't available with runtime constants. For example, whenever gravity is used, the compiler can simply substitute the identifier gravity with the literal double 9.8. When you declare a const variable, the compiler will implicitly keep track of whether it's a runtime or compile time constant. In most cases, this doesn't matter, but there are a few odd cases where C++ requires a compile time constant instead of a runtime constant. To cover these cases later as we introduce those topics. Constexpr, not sure how to read this, but to help provide more specifically, C++ 11 introduced the keyword constexpr, which ensures that a const must be a compile time constant. Expression. Yeah, thank you. Const expression, we're just gonna say that. Some words are really annoying to read. Especially coming from a different language. Best practice, any variable that should not be modifiable after initialization whose initializer is known as at compile time should be declared as const expression. So any variable that should not be modifiable after initialization and whose initializer is known as at compile time, so right when it's compiling before it runs, should be declared as const expression. I think many people reading them out loud, like you anyway. Yeah. Any variable that should not be modifiable after initialization and whose initializer is known at compile time should be declared as const expression. Any variable that should not be modifiable after initialization and whose initializer is not known at compile time should be declared as const. Yeah, so okay, this makes sense. Naming are const variables. Some programmers prefer to use all uppercase names for const variables. Others use normal variable names with a k prefix. However, we will use a normal variable naming conventions, which is more common. Const variables act exactly like normal variables in uppercase, except that they cannot be assigned to, so there's no particular reason they need to be denoted as special. Symbolic constants. In the previous lesson, literals, we discussed magic numbers, which are literals used in a program to represent a constant value. Since magic numbers are bad, what should you do instead? The answer is use symbolic constants. Symbolic constant is a name given to a constant literal value. There are two ways to declare symbolic constants in C++. One of them is good and one of them is not. We'll show you both. So this brings me the question of what if you want to change the magic number that you assign to? I'm not sure how often this happens, even when I'm writing on different languages that assign a variable to equal another variable times a number, and then I want to change that, but yeah. Yeah, it definitely requires a lot of stamina to read out loud. And that's why I'm not gonna do this when I think sometime, probably either Saturday or Monday or Sunday, I'm gonna read a lot of hours. I'm gonna try to read a lot of hours. And then it is impossible to read out loud everything. It just gets exhausting. But it's better to read out loud because you retain more information. Because you have to pay attention more. Oftentimes when I'm reading and I'm just reading a normal book, my mind starts deviating. And it's funny to actually notice that when I'm reading this here. A lot of times I have the tendency of thinking about random stuff while I'm reading. And then because I'm reading out loud, I'm forced to catch myself doing that. It's quite interesting. And I guess that all these deviations allow you to read for longer because you're not, it's like a way of your body saving energy, I think, and to make you think about other things. So you don't have to pay attention because focus makes you waste more energy, but then you retain less. So it's interesting to know that. It's kind of like a form of meditation. But using objects like macros with a substitution parameter as symbolic constants. We're going to show you the last desirable way to define a symbolic constant first. This method was commonly used in a lot of older code, so you may still see it. In lesson 2.9, you learned that objects like macros have two forms. One that doesn't take a substitution parameter, generally used for conditional compilation. One that does have a substitution parameter. Talk about the case with the substitution parameter here, that takes the form define identifier substitution text. Whenever the preprocessor encounters this directive, any further occurrence of identifier is replaced by substitution text. The identifier is traditionally typed in all capital letters using underscore to represent spaces. Consider the following snippet. Find max student per class 30. When you compile your code, the preprocessor replaces all instances of max student per class with the literal value 30, which is then compiled into your executable. So it's kind of like creating a const using this. You'll likely agree that this is much more intuitive than using a magic number for a couple of reasons. Max student per class provides context for what the program is trying to do, even without a comment. Second, if the number of max students per classroom changes, we only need to change the value of max students per class in one place, and all instances of max student per class will be replaced by the new literal value at the next compilation. Consider our second example, using hashtag define symbolic constants. In this case, it's clear that max student per class and max name length are intended to be independent values, even though they happen to share the same value 30. That way, if we need to update our classroom size, we won't accidentally change the name length too. So why not use define to make symbolic constants? There are at least three major problems. First, because macros are resolved by the preprocessor. All occurrences of the macro are replaced with the defined value just prior to compilation. If you're debugging your code, you won't see the actual value, e.g. 30. You only see the name of symbolic constants, max student per class. And because these defined values aren't variables, you can't add a watch in the debugger to see their values. If you want to know what value max student per class resolves through, you have to find the definition of max student per class, which could be in a different file. This can make your program harder to debug. Second, macros can conflict with normal code. For example, if some header.h happens to define a macro named beta, this simple program would break, as the preprocessor would replace the int variable beta's name with whatever the macro's value was. Thirdly, macros don't follow normal scoping rules, which means in rare cases, a macro defined in one part of a program can conflict with a code written in another part of the program that it is wasn't supposed to interact with. Avoid using define, #define to create symbolic constants macros. Better solution use const expression variables. Better way to create a symbolic constants is through use of const expression variables. Because these are just normal variables, they are watchable in the debugger, have normal scoping, and avoid other weird behaviors. So the downside of using the other one is the scope, very much, and that you can see them, and it's harder to debug. Best practice: use const expression variables to provide a name and context for our magic numbers. Using symbolic constants throughout the multiplier program. In many applications, a given symbolic constant needs to be used throughout your code, not just in one location. This can include physics or mathematical constants that don't change, or Avogadro's number, or application-specific tuning values, e.g. friction or gravity coefficients. Instead of redefining these every time they are needed, it's better to declare them once in a central location and use them whenever you need it. That way, if you ever need to change them, you only need to change them in one place. There are multiple ways to facilitate this within C++. We'll cover this topic in full detail in lesson 6.9. Sharing global constants across multiple files. Yeah, I think I'm already forgetting a little bit about the scope and the header files. But there was something that to define, and I forgot a little bit about that. Some special methods. I'm gonna have to revisit that at some point. But I have a lot of stuff to do off stream now, so I'll end here. And then I'll probably come back either tomorrow or the next day to keep reading this. So see ya.